the definition of a hyperbola is very similar to that of an ellipse, except that we're going to change the word sum for difference. It's the set of points P in a plane such that the difference of the distances from P to two fixed focal points is constant, rather than their sum. Now there are two formulas for a hyperbola that you see here, one beginning with the x squared, the other beginning with the y squared. In both cases, I want you to note here that a squared is the first denominator, and I'm going to write that down. Back with the ellipse, a squared was the larger denominator. For this, we're going to say a squared is the first denominator. When x is listed first, I like to say x is in control. This hyperbola is going to open left and right with the foci inside, and when y squared is listed first, then this hyperbola is going to open upward and downward instead. So the order of the fractions is important, and you know subtraction is not commutative, so you do need to pay attention to this. To find the foci, instead of using c squared equals a squared minus b squared, you're going to use c squared is equal to a squared plus b squared. In other words, when there's a minus sign between your two fractions, a squared and b squared will be added together, whereas for the ellipse, when there was a plus sign between your two fractions, you will find the difference between a squared and b squared. Okay, now let's go and graph our first hyperbola. We need to identify first where the center is going to be located, and don't fall into the trap of grabbing the 2 first. Go to the x fraction first. Find that plus 1 and change it to a minus 1, and we'll have minus 1 comma 2 be the center of this hyperbola, which I will be plotting right there. Now, we notice that y squared is first, and I like to usually off to the right or somewhere nearby just draw myself a little sketch saying, okay, this baby's opening up and down as a reminder to myself. Now I'm going to look at my two denominators. The 16 is beneath the x fraction, and that square roots to a 4. And the 4 is beneath the y fraction, and that square roots to a 2. So just like an ellipse, I'm going to go up and down 2 because 2 is in the y fraction, and left and right 4 because 4 is the denominator of the x fraction. And if this were an ellipse, we would now have 4 points through which we would draw this curve. But this is a hyperbola instead. So what we do is we draw ourselves a little box which goes through those 4 points that we have drawn previously, and then we draw in the diagonals of the box, and these lines will be our asymptotes, which we will use as guidelines for the hyperbola we're about to draw. And since we've already said that this hyperbola opens upward and downward, we're going to start at the 2 points above and below our center, which are located on the box we've drawn, and then we're going to draw in our curve, allowing the asymptotes to be our guide. So there's our upper curve, and here comes our lower curve, going through and touching the box at those vertices. So we probably would like to name the vertices for this curve. And those vertices are located 2 units above and below the center. So I'm going to add and subtract 2 from the y-coordinate of 2, and that will give us -1, 4 when we add them, and -1, 0 when we subtract them. We then want to know where are the foci for this curve, and they'll actually be above and below. Inside the curves will wrap around them, so to speak. So we're going to calculate c squared is equal to the sum of the denominators, a squared plus b squared, and this will be 16 plus 4, which is 20. C squared is 20, and then square rooting both sides of this equation, we now have c is equal to plus or minus 2 root 5. Now, since the vertices were above and below, and this is a vertical hyperbola, we will be moving up and down the 2 root 5 from the center. And putting this clue together, we now have the foci to be located at -1, comma, 2 plus or minus 2 root 5. Okay, there's another thing we want to be able to calculate from this problem, and that is the equations of these diagonal asymptotes. You know that all lines can be written in point-slope form as y minus y1 equals m times x minus x1. And we always also know that the center, if we look at our picture, the center will be a point that's on both of these asymptotes. So that will be the point we're going to use in this point-slope formula, and we will have y minus k is equal to m times x minus h. Now the m is going to either be plus or minus the a over b or the b over a, so I'm just going to write plus or minus m for the moment, and we will deal with that as we need to. Y minus k from the original problem gives me y minus 2, and the x minus h we know to be x plus 1 looking at the original problem. Now let's go back to our drawing. We had gone up 2 and over 4 for one of the asymptotes and down 2 and over 4 for the other one, looking at their slopes. So now we know up and down, plus and minus, 2/4, which will reduce to 1/2, and that in a very compact way is a way of writing our two asymptotes. We also could split this up and say y minus 2 is equal to 1/2 times parentheses x plus 1, or y minus 2 is equal to 1/2, forgot my equal sign, 1 minus equals -1/2, sorry about that, times x plus 1. And then do some distribution. Y minus 2 is equal to 1/2 x plus 1/2. Let's finish this side first and add 2 to both sides. Y equals 1/2 x plus 5/2 would be one of them written in slope-intercept form. The other one, y minus 2 equals -1/2 x minus 1/2. And adding 2 to both sides, we would have y equals -1/2 x plus 3/2. So if you want it written in that form, you can have it written in that form. If you want to leave them in point-slope form combined together, as I've got my pen pointing to that, that is fine also.